All right, so I'm very happy to have a Karthik CS from all the way from Rutgers.
New York.
All the way from New York. Okay. All the way from New York. To talk to us about it's like a survey-ish talk.
Yeah.
About the parameterized complexity and stuff.
Right.
PCP related, I guess. Okay, feel free to ask him as many questions as you like. And, he has a lot of material planned, and my goal is to make him go through only half of it. So.
I always enjoyed presenting to Edith, and now I get an extra bonus, so I'll enjoy it for sure. So I have a lot of things like personal thoughts on certain ideas here, so I wrote it down. This is a very ambitious plan. I'm trying to sort of tell a story of evolution of certain techniques to develop Hardness of Approximation for this area called parameterized complexity. So I'm going to try to, so this is like sort of the outline of the talk. So first is sort of like tell what is this area parameterized complexity. Like what are some interesting problems people study, what's the focus, and so on. And then we'll look at some research approach on how people tackle problems typically in parameterized complexity. And then, what did I want to say? Some selection of major results. Plus my own sort of personal take on these things. And then I'm going to set things up with defining CSPs. So what are two CSPs in this context, and why are they interesting, and so on. Then I'll talk about set cover problem, how through hardness of approximation, starting from no gap to CSPs, then about clique, and then finally about gap to CSP. There's a reason I write it in this specific way, because unlike in the NP world where the PCP theorem sort of came first and then these sort of followed, sort of one of the insights is that you don't need a PCP theorem to get gap results for clique and set cover. So you need some weak version of gap in CSPs, and we'll see what these are. Okay, so this is roughly the outline. I'm happy if I can cover everything till here and some part of this. This is like roughly halfway mark, or slightly over half. Okay, so we have this theory of NP completeness. Some problems that we care about, optimization problems, are intractable, where our notion of efficiency is polynomial time. And there are many ways to cope with this thing. Like you can either ask that I'm interested in certain structural, like I know things come from a certain distribution, or I'm happy with compromising on approximation factors. But there is another way, which since the 80s people have been doing, which is parameterized or multivariate analysis. Like there are certain maybe parameters of the problem that are of interest. So for instance, if you have a graph problem, let's say like clique, you might be interested in the parameter which is the size of the largest clique, or maybe the tree width of the graph. So there are several structural parameters that are of interest. And then you want, assuming these structural parameters are small, you want to know, can I solve this problem efficiently? So that leads to this area called fixed parameter tractability. So just a couple of examples. Vertex cover, parameterized by opt size. So you're given a graph and you're asking, is there a vertex cover of size k or not? And you're allowed to run in time f of k times poly n. So it's an FPT. If you run in time f of k times poly n, and f can be any computable function, n is the size of the graph.
And K is 0.
And k is the opt.
Yeah, FPT is fixed on the plot.
Yeah. And the way sort of you can see this is
What is the opt again?
the size of the optimum solution, which is here the smallest vertex cover for the graph. So the way to see this is just you take an arbitrary edge, you know that one of its endpoints has to be in the opt. And so you branch. Basically, if you take an edge u comma v, either u is in opt or v is in opt. If u is in opt, then you add it to your solution and you remove all the edges that it covers and then recurse on the remaining graph. And the point being, you just have to go for depth k.
So you and V are vertices.
Right.
But they look like edges in the piece.
No, it's a tree. It's
It's a tree.
Yeah, very good. Okay.
confusing too.
Sorry. Yes. And so the point is you just do depth k, and either you have picked k vertices that cover everything or not. This runs in time 2 to the k times poly n. Again, it doesn't contradict anything about our NP completeness because 2 to the k is, yeah, when k is linear in n, this is tight. But it also tells us that the hard instances have to have this k linear in n. So,
Karthik, like the algorithm knows k or it guesses k, or it doesn't matter.
k is given, let's say, as parameter.
Oh.
Yeah, so it's sort of known a priori, k vertex cover.
I see, but you need to be uniform. Like it needs to, like it's not that like for one k I can do this, for another k I can do that.
Right, yeah, so you say
Yeah,
for
family
family.
is a fun.
Yeah.
You can also
For
use
family, for instance, that's
Sure,
fine.
it's like the same. It's the same algorithm, only it needs to.
Its runtime is, quantified by
Okay.
f of k times poly.
Yeah.
could like try all the possible values.
If you sure,
Right.
if it's
Another example is, for instance, if you're given a graph and you want to find a path of length k, so that also is a fixed parameter tractable. I have something else to say. Just to give something that's not parameterized by opt, for instance, if you took at vertex cover or clique or dominating set parameterized by the tree width, which is some measure on how close it is to a tree, then it's also in fixed parameter tractable in terms of that parameter. Okay, so great, but then we would like to know for which NP-hard problems is it not in FPT, and we care about these problems. And some candidates are like clique, when you parameterize by opt, so let's call that k clique, k set cover or k dominating set, and even k coloring. K coloring, when you parameterize by k, the number of color classes needed, is actually NP hard for even k equal to 3.
K set cover.
You are given a set system and you want to pick k sets that cover the universe. So k coloring, it's NP hard even when k is 3, whereas this is not true for these two. So you have things that are fixed parameter tractable, you have things that are NP hard, and then you have something in between. And these things in between fall in this class called XP, which is called slice-wise polynomial. I'm still trying to digest why it's called that. So this is all those which admit runtime of n to the f of t for some computable function f. So both k clique and k set cover are in XP. So we have this nice picture. You have FPT, then that's contained in XP, and then you have NP hardness. So far we are good, right? Now let me try to. These two are not really the same things, and let me try to give some intuition, and this can be formalized. If I give a solution to k clique, it's going to be k vertices, and then all you have to do is check if the k choose 2 edges exist in the graph. So that's like checking k choose 2 things. Whereas if I give a solution to k set cover on a universe of size n, you're going to give me k sets, but then I need to check n things, which depends on the input size. So these two are not really the same thing. And this is where this class of, or this complexity hierarchy, or W hierarchy, shows up. And just to show it short, this is the canonical W1 complete problem. And I will define what these are more. And this is W2. I'm going to formally define what W1 and W2 are, but in any case, you can just think of these two problems as there. Anything that can be reduced in FPT time. So your reductions are allowed to also be in FPT time. Let me define what an FPT reduction is. So we say that there's an FPT reduction from pi with parameter k prime. If the running time of this reduction is some f of k poly, the size of pi. So it runs in FPT time. And k prime is some g of k, some other computation. So you're preserving the parameter. It's just same like how in polynomial time, closed under polynomial time, this closed under FPT time. Okay. And so now you can either define it like this, that a problem belongs to W1 if it can be reduced to k clique in FPT time. There's an FPT reduction. A problem belongs to W2 if there's an FPT reduction to set cover. But I mean, you can also formally define it. Let me just show the circuit and then just verbally tell how the definition looks. So for k clique, we can think of the circuit looks like this. Do you like circuits done from bottom up or
Sideways.
sideways?
You asked for it.
Yeah, we just have to lie down like.
So we want to pick, so these are x1 to xn, and the ones correspond to picking it and 0 correspond to not picking it. So you want to pick k things. And then you have an and for every non-edge.
No. That's it.
I understand this.
You reached my limit.
So this is every non-edge. You have an and k in the graph, and you connect. Let's say it's one at xn. It's so on. Every pair that's not an edge. And then you have an OR. So this OR is 1.
What do you mean an edge?
Sorry, the circuit connection. I need to tell the wires of the circuit, right?
You're trying to guess the K-click, right?
I'm trying to guess the
n variables, 0, 1, and you want to pick k of them for which all the edges exist. Okay.
Sorry, I was thinking we're doing set cover, so we're doing
K-click,
Right.
yeah.
x1 to xn are what? The
But
vertices?
yeah.
Oh,
And I want to pick k of them
sorry, okay.
such that every pair has an edge,
Right.
or every pair does not have an edge. So
Right.
that's the way we are checking. So I look at all non-edges,
Mhm.
and even if one of their ands is 1, then the OR of these things will be 1. So the OR is 1 if it's not a K-clique. So I just take a negation. So this is how it looks. But
Mhm.
in particular, if I define a gate to be large, if it has span in more than 2. So if I look at any path from the output to the input, how many large gates do I have? 1, which is going to be this OR. So that's the 1 in W1. And let's just, for the sake of it, do it for set cover to see it's going to be 2. So x1, xn. And then this is all the sets, and you want to pick k of them. And you have universe as your OR gates. This is the universe. And you want to cover every one of the universe. And yeah, so this can be large and this can be large.
Oh, but you can always split a large gate into a lot of smaller gates.
Good. So the WT, like in general, is unit of constant depth circuit. And then you ask, how many number of things do you have? So that's the class. This is called Veft. The number Veft.
Left?
Yeah. So apparently it comes from stitching clothes. So when you have all these fibers like this, and then there's something that binds them, that runs through the whole thing. This is called a weft.
Can you spell it? Okay.
The weft of a circuit is the number of large gates from input to output.
I knew it.
Can you use it in a sentence?
Just did. The left of a circuit is.
Wait, Max, you know English, you know this word?
Oh, I've never heard of this. Not an SAT word.
You have to know carpeting.
Yeah. So it's the number of large gates that we have on any part. You take the maximum.
Kind of.
Yeah.
All right, nice.
So WT is basically take a constant depth representation and try to minimize the weft. So you get clique and W1, W2.
So you're saying that anything in W1 can be reduced to click, and anything in W2 can be reduced to
Set cover.
Yeah, right.
Also, the definition is like you want to find a satisfying Hamming weight that's most okay.
Right. So this you can think of it in circuit sat form. You want a Hamming weight at K. There are equivalent things in terms of Turing machines, but it's roughly the same. Okay, so this is done. So all of this is known. These are hard. So we believe that these classes are separate from FPT. In fact, it's believed that W1 is strictly contained inside W2, and so on. Good. So that means that for K-clique and K-set cover, there are no FPT algorithms.
You want to give credit to the originators of this theory? Okay, I probably not critical.
Sorry, I forgot to tell my disclaimers. Disclaimer 1, I'm presenting a lot of ideas and things.
No, just just have fixed parameters.
Oh, Fellow and Downey.
It's in the 80s, I guess.
Yeah, it started in the 80s. I guess the journal versions appeared in 95. But I need to say two disclaimers. Disclaimer one is that a lot of the things I'm going to say, like in the second half of the talk, are not written anywhere. And I tried to sort of put it all under a CSP narrative. So it's under one narrative and it's sort of told. So when you go and read it, and I'm also compromising on the strength of the result so that the technique sort of looks similar. So if you go to the papers and read, they will be trying to prove general or stronger results, so a lot of technical details. And
So
second,
you have a representative problem for every level of this W? For WJ, you have
You can always make a complete problem from
yeah,
this.
you're meaning natural,
Like
I
you
guess.
make SAT and be complete. Yeah, but the question is whether they are natural.
So there was a paper written about finding a natural problem for W3. So you can now, if it's a paper is writing just to motivate a problem, then it's like some graph problem, which is like, some extra parameters that they show as W3 counter. I don't think for W4 they know anything.
What is WP?
Sorry?
And also there's WP.
WP?
Yeah, so on top there.
Right. Oh, there is like, I think K longest common subsequence is, I think it's all the way up complete.
Sorry, P means polynomial here? What is it?
I don't know.
Yeah.
I'm not sure.
So the,
Historically, you know what the class NC, what is stands for.
Next class.
Next class, so what do you expect?
okay. And also, many times I'll give credit at the very end, just saying who proved what. Try to prove that. Okay, good. So now, for the next 10 minutes, I might say some controversial things. So please engage me here. Approximation.
So far, so good.
Yeah, so far so good, hopefully. Okay, so let's see. Let's start with clique. So in the NP world, we ask, clique is NP hard, can you approximate it? And fine, we can show something like, it's hard to approximate to n to the 1 minus epsilon, even push it a bit beyond. But then there are non-trivial approximation algorithms. So you can do better than n approximation, just output a single vertex. So you can do something to the extent of, I think this is the state of the art. Which is better than n. But then, okay, so this is my take, that I'm not happy with an approximation factor which involves n. What I would ideally like is something that's little of opt. If I'm telling you opt is something, so you can ask, is there something we can do for little of opt in polynomial time? I like this question a bit more than this.
So that's the controversial part.
Sorry?
Because that's the controversial part.
It's the beginning, yes. Yes, so that's like.
I don't want to shock you.
I'll slowly ease into the controversy. Yeah. But then, you can forget polynomial time, you can ask even FPT time, parameterized file.
We don't know.
Sorry?
We don't know the answer.
Oh, the punchline is thanks to
this.
this theory on hardness of approximation. Yeah, so for instance, under gap ETH, we can prove something, and weaker assumptions, we can prove something.
Yeah.
So the answer is no if you assume gap ETH, which I will define later. So that's a very nice thing to have. Okay, so that's one motivating question. But you can even ask this kind of a question, sort of more refined. Is there, so I'm telling you there is a k clique, and I'm asking for just a g of k clique, where g of k can be log k or square root k, some lower function.
Sorry, maybe it's a stupid question. Why is it not interesting even if it's just opt? Like, it'd be interesting to find a k squared clique when there's a k. Like, why little o of opt?
No, but
Then you find the bigger one.
Oh, right,
it's
right,
not-
sorry. Oh, yeah.
Is there g of k approximation?
No, but I understood the little o as the approximation
Yeah, yeah.
factor. Right?
Yeah.
Not the answer that you.
Yeah, the
Right,
approximation factor.
I mean,
It's the
to
approximation
find the
factor.
clique that's little o of opt, even I can do.
One vertex is opt factor, so
Right.
Finding which is little omega of one, so the same.
Sorry?
Like finding which is little omega of one.
yes, any little omega of one, find me
Yeah.
something promising you that there's a k clique.
Yeah.
So for instance, you can ask this question: is there a g of k approximation in time n to the little o of g of k? Or k over g of k approximation.
Zero of g of k is another g of k.
Sorry?
Wait a minute. Zero, k over g of
So
k.
because
Okay,
if I run in this time, I can just brute force and check all these cliques of size g of k. Can I do something slightly better? Well, I'm promising there is a k clique. Yeah, the answer for this is also no. Like assuming gap ETH. We can get something close to this assuming ETH without a gap. So these are like some motivating questions for this. Okay. One last motivation is I'm motivated with set cover. So yeah, same thing, set cover. We know Lannan approximation when n is the universe size in polytime. And this is type, assuming p not equal to p. But what if I'm allowed FPT time? Can I do anything better? So is return of Lannan in FPT time possible?
Lan n or lan k? Lan o.
Yeah, Lan K also, but even Lannan, like I'm being generous.
Zero, so yeah.
Yeah. So I mean, I could ask instead of this, I can be more ambitious and ask, can you do some f of k approximation? Like,
So you're asking f of k times little o of ln n. That's what FPT times means.
So it means that if there is a set cover of size k, find me one of size say square root log n ln n times k in FPT time.
Oh, this is the approximation factor, okay. That makes the running time and
And you can ask instead of FPT time, I can ask n to the k and like brute force search and so on. Okay, and I can instead of this, I can ask even more ambitious things like any f of k independent of n. Yeah, so we'll see answers to all these during the talk, hopefully with full proofs. At least 3 questions. Okay. Who's there? I erased the outline so that if I deviate, no one. So the research approach roughly looks like this. I mean, of this whole program of hardness of approximation and parameterized complexity, or even the fine-grained questions that are there. I think there are many assumptions, but let me focus on 3. One is gap ETH. The other is ETH and W1 not equal to FP. The distinction is that this has a gap. I'll tell what these are.
Some people in the audience don't know what.
Yeah, I'll define
PCPs
them
is,
now.
yeah.
And this is no gap. So W1 not equal to FPT is well defined. It just says that K-clique does not have FPT time algorithms. ETH says that there exists some epsilon greater than 0 such that no algorithm running in 2 to the epsilon n time can solve 3SAT on n variables.
So this is a hypothesis.
There's a hypothesis. It's exponential time hypothesis. And gap ETH says that there exists some epsilon delta greater than 0 such that no algorithm running in 2 to the epsilon n time can distinguish if a given takes as input a 3SAT formula and either it's satisfiable or if every assignment violates epsilon delta fraction of the clauses.
Did you say that ETH is equivalent to this statement next to it? W1?
Yeah, ETH, no, I haven't said that.
Oh,
These
okay.
are just 3 assumptions.
Okay.
And they are placed them in order for a reason. It is known that, I mean, probably easy to see that gap ETH implies ETH. And ETH implies W1 not equal to FP. So this is the weakest assumption to make. Followed by this and followed by this.
So why do people believe in gap ETH?
Why do people believe in it?
Or they don't?
I like so it's not a conjecture, it's a hypothesis. And I think the value of it is if it's false, we learn a lot. If it's true, it implies a lot, so we learn a lot. So it's great to have a hypothesis like this.
And people believe in it.
Some people believe it.
Do you believe SETH?
I don't know.
It's a good assumption
Yeah,
because it can
like
maybe
you said.
vary.
I mean, if you have linear PCP and you assume
like
ETH, then you can get gap ETH.
Right, but
So maybe
suppose,
that's
right, that's a good point. So you know gap ETH, but with weaker parameter.
Right. So
Not
instead of
interesting for this.
right, if it instead of epsilon n, it was n over polylog n, we know this.
Right.
But it doesn't give any more. It doesn't give any implications that I want for exceeding. So
Is there, like, where's the polylog become so important here?
when you see a reduction, the way it typically goes is you have 3SAT, and then you partition it into k parts. Where k is your parameter. So typically, it's like some large constant, and then you want to rule out n to the little o of k time, which only gives you 2 to the little o of n. So if you have polylog, it implies nothing.
Okay.
I mean, I'll try to say a bit more.
Maybe like rule out like an end, I don't know, like k over log or something.
No, because k are they're all constants. So,
Okay, yeah.
but if you assume k is like I don't know, like log n or something like that, when you merge the two things, then it might imply something at some point.
But you don't have control over f of log n.
Sorry.
This f take polynomial.
Yeah, you don't have any control over the f. So this can be. Okay, so there are 2 lines of research using these 3 assumptions. The first line is to just rule out FPT algorithms. So you have some problem pi that you care about, and you want to say no FPT. If I want to say no FPT, ideally I want under this assumption. But sometimes it's very hard, and you're trying to do out approximation algorithms in FPT time. So, sort of the guideline is take the strongest assumption, try to prove this. At least that gives some sort of evidence that this is possible, and then try to weaken it, try to get it under this, and then finally this. So this is one line of research that happens. The other line of research is I want to say nothing better than exhaustive search is possible, even for approximating it. And for that, so let's say it's here. You have phi no better than exhaustive search. And first, again, it's a gap problem. So you try to prove it using gap ETH, and then try to weaken it to prove it using ETH.
Don't try too small because the people here can.
Oh, yes.
The font size, yeah. Up to now it was
don't
great.
have the screens. No better than status.
I mean,
I mean, like until the.
how come that doesn't make sense?
Yeah, you want to say it's into the omega k.
How can I go?
Karthik. So when you write only these three assumptions, like essentially people don't know how to gain nothing from anything in between ETH and W1 not equal FPT.
Right. I mean, at least I don't know a popular assumption that's in between them. Although there are candidates like K-sum hypothesis and so on. Yes.
So here your f of k is like an arbitrary function.
Right.
How much it breaks down if you decide that f of k is to be, I don't know, most like 2 to the order k or 2 to the poly k or something like that?
So what breaks down if I
like because the vertex cover algorithm is 2 to the k. And
Right.
maybe, I don't know, maybe I decide that 2 to the 2 to the k is way too big and I don't want to consider that valid. So,
There are many algorithms that follow from, for example, the Seymour-Robertson characterization. This general theory about graph minors, where the function f of k is, I don't know, maybe flip the exponent. Yeah, but it makes sense what you suggest.
Yeah.
Of course, when you have something, you want it, but
the issue is this notion of reductions, which are sort of these closed under these things. You'll have to be very careful when it breaks, how do you handle it and so on. Okay. So this is the framework roughly, and it has led to a lot of success. So initially things were proved as assuming gap ETH, and for most of them we could even recover it using ETH and W1, maybe into slightly weaker factors. So this is like a nice blueprint of how to go about these things. Okay, so we'll do that on Sunday. Okay, next another set of controversial. Last set. This one will be slightly more spicy, hopefully. Let me choose my words carefully. PCP theorem was a very strong result. But maybe it was too soon.
we don't normally say glorious, but
That the world has ever seen.
But maybe it was too soon. Like in the sense that it's like a very powerful tool, and, which was used to solve things which could have been solved with weaker things. But of course, when you already have a heavy hammer, you try to hit it. So in the 90s, people just tried to use PCP theorem to prove everything. And they did get optimal results. But then you can always ask, what is the weakest amount of work I need to do in order to obtain a specific result? So for instance, I'll write 2 leading questions. Assuming gap clique is NP hard. recover PCP theorem. And like I'm saying, 1 versus 1 minus epsilon for clique is NP-hard. Can you prove that gap to CSP is NP-hard?
What do you mean 1 versus 1 minus epsilon?
So there is either a clique of size k or there is no clique of size 0.99k.
Right.
And now we need to say something about 2 CSPs from this. I don't know how to say anything, just
Wait, that's an open ball.
hope so, yeah.
In,
No, okay, you didn't give us the title of your plan. This sentence, that's all.
Oh, so this is like a leading question. Can you do this?
So just to say, there's this the FGLSS reduction that converts between a CSP and a clique instance. It's just a bit structured, like the kind of graphs you get from a CSP when you apply this FGLSS reduction gives you a gap clique problem, and you can go both ways, but it's a bit structured.
Right.
So you're asking, what if I remove the structure?
Right. And hopefully I will show some things on how to prove gap clique without actually proving gap CSP. Sort of highlighting, I will give you a CSP where there is no gap, but you can get constant gap for clique. Sort of highlights that you might need just weaker things here. So just assuming this might not be enough. So,
there were very few, but nevertheless, inapproximability results before the PCP theorem.
right.
For example, Gary and Johnson proved that it's NP-hard to 4-color, 3-color bar graphs. Simple combinatorial reduction, but anyway, it's inapproximability.
Right.
And actually, coloring is one of those problems that even in the past 10 years, we had some results like that. You can, and be hard to prove to 6-color or 3-color graph. That's
Is that the fact that it's like a minimization problem and PCPs are typically maximization?
I don't think so. I think it's more like, okay, I'm not sure I understand those reductions well, but it seems like if you find the right gadget, you can do it.
Yes.
And
So this is not in the same as the baby PCP theorem.
what's the baby PCP there?
It's like if you want to just get something for min CSPs, where you want to minimize the list size, you can do it using just some direct product testing. There are some results in the last few years based on this.
So, okay, so Irit mentioned that like you can convert PCPs to gap clique problems, and like if you knew that these gap clique problems were hard on their own right, and you'd be able to convert this back to a PCP. Like, are there weaker structures that you can impose on gap clique to recover some kind of PCP theorem? Is it just the FGLSS, or can you kind of play with the?
Yeah, I guess you need some version of, like for instance, let me say this, like if you had a CSP where in the yes case, everything is satisfiable, but in the no case, something like for a constant fraction of the variables, one constraint fails. I think you can get gap clique, but it doesn't say gap CSP. And we'll see something like this.
So, like for every large enough set of the variables, you will see a failure.
Right. The point is clique only needs one thing to fail, and not a constant fraction. But the same question I can also ask for set cover. The nice thing is a PCP theorem equivalent for the FPT world is open. So we can actually try to answer this because we don't have anything to rely on. And that's what I try to show, that we can get some version of gap set cover in the FPT world just using error correcting codes. And using local decodability of Hadamard codes, you can get gap clique. You don't need anything more than that. So these are like two things I want to show. And then finally, we have some progress on getting PCP theorem for FPT assuming ETH, so I'll talk about.
Sorry, I'll take you back. So you claim ETH implies FPT hardness of W1. Is that something that's easy to see, or?
Yeah.
Yeah. You take, so if you have a formula phi and it's on M clauses, then you partition the M clauses into K parts. So you have part 1, part 2, part K. And for each node corresponds to a partial assignment that satisfies all these set of clauses. And then you just do consistency. You get a K-clique instance. So, yeah.
And does it mean that whole hierarchy is tight or is strict or?
Yeah, this is something called M1. There's a complexity class. It's intermediate between FPT and W1. And sort of sits in between the two things.
Gotcha. But so does it imply W2 is adequate to W1 or?
No, it doesn't say anything about that.
Do we have any assumption that implies?
Not that I know of.
And this is for, I don't know, ETH of sigma 2 formulas and the W2 nodule.
Yeah. I'm not familiar with how to separate in the hierarchy. Okay, so let me say quickly a few things. So I said about set cover, cat clique. Let me write two results, which I won't talk about, but sort of fits in this framework of contributions. Let me write the less impressive possibly result first. Assuming ETH. No. With a clique in the NP world. And this is a strictly weaker statement. The catch is I can prove this whole thing completely with like self in less than 2 pages. So if you want to show it in class and you have PCP theorem and you want to show how gap is created, you can show a proof of this less than 2 pages.
You expect a much bigger than into the log.
Right. So the point is, I'm going to use Hadamard codes, blow up not exponentially, but 2 to the square root 10. And all I use about Hadamard codes is that if I want to decode a vertex I, you query at a random point A, and that's it. Not even the linearity testing, none of those. So this can be done. This statement itself is because of, so the technique is because of Chen. But this observation that the statement holds is from an undergrad whom I worked with in the summer. That you can take that thing which was for the FPT world and get this statement as well.
Sorry, are we supposed to?
You can abstract the authority of Hadamard code you need.
Yeah, it's like
better code.
You need some smooth, locally decodable code that is 2-query. Yeah, 2-query is interesting. It will come up again. Yeah, one of the things here we get is we learn a lot of hacks around FGLSS. Like how can you tweak FGLSS to squeeze something more than what you could do before. The other result, which I want to say, is because of then so we know that set cover is NP hard to approximate to Lannan factor, but the sets, the opt size is close to n, like it needs to be polynomial in n. So what if I tell you the sets are large and you just opt is like polylog n? Can you say something? So the proof breaks, like we can say nothing from the current proof techniques, but you can show the following. It's a very interesting statement. Assuming W1 not equal to FPT. No polytime algorithm. For approximating field set covers. To factor little o of log n log n. Even when k is log n over log n of q. So these kinds of statements we couldn't say before. The proof of this is extremely nice. It uses what is something called now threshold graph composition. It's an extremal combinatorial object. There's a very non-trivial way to compose it with the input, and you get a gap instance out of it.
Karthik,
Yes.
is the fact that you need a two-query decodable with locally decodable code just because the bench has two endpoints?
Yes.
So if you wanted, I don't know, approximation for like a 3 uniform hypergraph,
You would need three queries.
Okay, and then you could really push this higher and use a better locally decodable code.
Yeah, I think that's true.
Or something.
Okay. So now we'll get into techniques and how to prove things. So the outline is still the same. I'm going to define now what a 2CSP is, how it is looked at in the FPT world, and what is the smallest thing we need to do to get gap set cover, a little more to get gap clique, and a bit more to get gap 2CSP.
Are you aiming to show us part of the proof of these things or?
A proof of this, yes.
Okay.
Yeah, I mean, some maybe stronger version of this actually. This, I might speak about it in the Princeton theory lunch in 3 weeks. Some general version of this. Like, yeah, this is a technique which is sort of very new, and I want to sort of talk about what all results we can get from this technique. So 2CSP. Here, given some constraint graph, you have some alphabet, and you have a set of constraints. So every edge is a constraint on 2 variables. And yeah, I think of C as CE, which is and your goal is to find an assignment. Sigma is an assignment, and the value of the assignment is just the fraction of clauses that are satisfied. So we write it using probabilities.
Three coloring is an example.
So three coloring is an example where the constraints are not equal to, like the pair don't. But in the FPT, right, so this is 2CSP. We can talk of gap, epsilon gap to CSP. And the goal is to distinguish between the case when there's a satisfying assignment versus every assignment violates at least epsilon fraction of the constraints. And if epsilon equal to 0, this is exact to CSP. From the parameterized world, we are interested when the parameter is V, the number of variables. Why? Well, that the most naive way to solve a 2CSP is to go over all possible assignments, right? And that will take us time. Where k is the number of variables, it takes sigma to the k, and you're asking, is there an f of k times polysigma algorithm? But also, if you look at a CSP, let's say these are variables, but then I can actually look at all the labels that the variables can get. And then think of it as a graph on these things. Then you just get a clique instance. So there's a natural way of going back and forth between CSP and clique, k-clique. FGLSS, you would have to take like the constraints and look for consistency. Yeah, it's a small. This distinction is important for the reduction because it critically uses CSP properties.
Like you want statements that say like, here's a graph, I can just draw it on the board like one graph, not the infinite family or something like that. And now I can like vary the CSP itself on the graph like as.
Sure, you can think of the complete graph.
Sure, but like my question is kind of you're doing parameters complexity and you're taking V as your parameter. So you're just saying like look at the click on V, and now like the only thing that's changing is like sigma and the constraints, right. And like you want an algorithm that runs just on this like single graph.
Right.
I was confused about the CSP. I mean, any KCSP you can convert to 2CSP kind of easily.
Right, by looking at all possible k tuples.
No, by having a variable for every constraint and comparing two constraints if they have shared variable on your equation.
Right.
So it's not like such a big difference.
Sure. Yes, I agree.
Okay.
Yes. No, I agree. Okay. So the way I keep viewing this, of course, exact to CSP.
By you are blowing up the parameter in this reduction.
Yeah, but
am I really like?
Number of constraints could have been big. You want a constant number, not the number of constraints, size of the graph.
No, it just blows up by k squared.
Yes.
Like k becomes k squared,
K squared. Okay.
n becomes n squared.
Okay.
And exact to CSP, we know two things. One, it's W1 complete. And two, if I assume ETH, it takes n to the omega time is needed. So this is sort of optimal up to constants in the exponent. So that's our starting point. And we want to prove results based on that. I typically keep this view in mind, which is this matrix, which is a witness for what are the k assignments. So this would be numbered 1 to k. And let me think of sigma, size of sigma, as some n. And so this I can think of it as log n bits. right? So this would be like a witness, and then what you would check is that for every constraint, which is every pair of some pair of rows, does it fall in the set that was specified in the input? Okay. Let me spend 10 seconds seeing if I want to go from this to a gap version, what would be the first bottleneck using standard PCP tools? Is that what you would want typically to do is look at every constraint, write it down as some kind of a circuit computation, and then you sort of use PCPs on top of these circuits. But if I write a circuit on any constraint, it has log n, 2 log n bits. And so the CSP size eventually is going to be some function of n. And that is not allowed. You need to stay in K. So that's the main bottleneck we are trying to fight each time. So you need to work around handling the fact that, I don't have any handle on how this looks. How do I do something?
Even if you have a handle, suppose it's still coloring, so you know what it is.
Right. But I need more. I need more structure than just.
Yeah, even three coloring, you cannot obviously get rid of the dependence on n.
So 3 things we will do now. One is the first thing is okay. I can't in first 2 cases I can't do anything. So let me work around it without proving anything for CSP. And the third one is fine. I can get a hard instance of CSP where I have an handle, and there I could use standard PCP machinery. So these are the 3 things we need.
So what are you proving? What are you trying to prove in these 3 stages?
The first theorem will be about getting gap set cover and using just error correcting codes. So theorem, FPT reduction from exact to CSP to gap. I haven't told what the gap we get is, but we'll figure that out later. K set cover. So this CSP has, say, K prime variables. So this K and K prime are related. There are more of the nice talks this side. How are we doing on time?
You're doing well. It's 11:30, so if you want to take a break.
Yeah, we can take a break, but we're not doing well.
Okay. What happened to the board?
I saved time.
Okay, all right.
Okay, so we start from 2 CSP. So there is a standard way of looking at it, which is you have all the constraints here and all the variables here. And let's label that V1 to EM, V1 to EK, and you're just doing consistency check between the two. But at the same time, let me keep in mind I have K things here and log n things here. This is my witness. So in the yes case, I would pick 2 things, 2 rows here, and then assign it to this each of them, and then 1 row for each of them, and then you just do overlap. Like if I have 2 rows and you have 1 row that is one of my 2 rows, then we check if they are the same.
But you need to also check the constraint itself.
Right, and I only allow the pair of rows here which are satisfying the constraint. So that's my alphabet. I just force it through the alphabet, and then it's just consistency. So this is the way one can look at it. Here is an alternate way. Instead of asking for rows, a single row here, let me ask for a column. So I do some kind of row column consistency check. So what that would be is, let me call this columns, and A1 up to A log n. And the alphabet here is going to be like the size of this is going to be 2 to the k, because anything here, there are k bits, so it's 2 to the k, and the consistency is still the same. So this, a particular guy here will have access to this row and this row, and one of this will have column this one. So let's just check consistency on this point and this point, right? So we will still get it that in the yes case, everything is satisfied. In the no case, one constraint fails. Okay, but how does this constraint fail? It's going to be failing on like many locations in that specific row. So if we just encode this using an error correcting code, it's going to amplify.
You encode every row.
I encode every row. Right. So what I will do is I will just take some encoding of this. And now let's say the encoding is some function, I need a function, ENC, which takes 0, 1 to the log n and maps it to some 0, 1 to the r times log. Now, r is like 100 or million, whatever. It can even be some function of k. So we get this thing. And now it's no longer a r log n, but let me write a r log n. And I still have the same thing. So in the yes case, what do I have? In the yes case, there is some sigma such that all in E, I'm going to just write sigma of E to mean the pair. When E is u comma v, it's like the pair of things. So we have this, and now from this I can obtain a label for this and a label for this, which is the label for this is going to be still whatever the pair is, and the label for this is encode whatever these vertices are, and on that coordinate look at it. So I can obtain some sigma prime from E to sigma, which is the sigma prime of let's say u comma v is just sigma of u comma sigma of v. And on the right side, you have some let me see, sigma prime call, which is taking everything in call and then mapping it to. So I used F2, but you can typically use FQ, whatever, it's fine. F2 to the K, which are the K things that are there. And it's going to look like this. Sigma prime call of AS is going to be, so whatever these things are on the S coordinate, so let me write it as sigma of V1 on the S coordinate, sigma of V of this. And this satisfies all the constraints.
Wait,
Oh, sorry,
where's the
encoding?
the encoding of this. It's too much text.
So you take sigma of V1, you encode it, and then you take the S coordinate.
Right. So in the yes case, we have everything satisfies. In the no case, ideally we would want that a constant fraction of the constraints fail, but that's not true. But we do get something out of this. Call
You lose just a factor of k, right?
Yeah, but that's
Yeah, no, yeah,
Okay.
I understand.
call AS good. So AS is some variable on the right under an assignment to the right side. If all of its constraints are satisfied, right? And what I want to claim is that in the no case, a constant fraction of these will not be good. So you'll have at least one being violated. In the no case,
Sorry, can you repeat the difference? When do you call AS good?
if I look at some assignment here and here, and I look at AS and look at its M constraints, and if all of them are satisfied, then I call it good. Oh, I didn't finish the definition. Sigma of so let's let me just put a notation saying E. Let me call this HF. I'm going to use notation and say this belongs.
But you said that you don't have to use binary code, right? If you use a QR code where Q was much bigger than K, you could make the distance like
Right.
1 minus 1.
We can do it. We will do that.
K squared, and then you can take a union bound over there.
Right.
So this would, is this what you're going to do?
Yes.
Oh.
I'm going to just use Reed Solomon codes eventually.
Yeah.
That's to get like arbitrary large gap. So in the no case, I want to say that this is not possible. That in fact, the distance of the code is the number I can have. That's it. So suppose I had some assignment such that number of AS that is good is greater than 1 minus the distance of the code times R log. Then I claim that something is off because I know that if I take sigma E, I should have some place where I have for the same variable 2 different assignments because I'm in the no case. And now, so there is some row where one of them writes something and the other one writes something else. And they're going to differ on the distance of the code. And for all those columns, one of those constraints will be violated. This is fine.
So it means that all those columns will have at least one bad neighbor.
Yeah.
And it's not going to be good.
Good. This is fine. Okay. This less minimal writing, I think I can do something.
No, sorry. No, it's just that we're saying a lot of statements, and in a minute I will forget.
Yeah. So
suppose such that, then.
So now look at sigma E, right? There exists some V in V such that for some, sorry?
I don't need the proof, I just need
maybe
in the
instead of
statement,
suppose,
the
right?
number of good things is less or equal to, is that the statement we are?
Oh yeah.
Yeah, just erase the suppose and write and you reverse the.
Yes.
Okay, so now I'm happy.
That's it. Good. From this, because we are looking at set cover, which is a minimization problem, I want to obtain some minimization kind of result here. So I will allow multiple assignments to every variable. And I call someone good if there is some assignment I can pick for everyone such that all the constraints are satisfied. So I allow multi-labeling now. And I want to just derive from this in a black box way something. Let's call this list no. Suppose I have I need to pick a set x1. So this is all possible labels that I'm allowing for these ones. X1 to xn such that for all s in R log n, so for every right variable, there exists some this was probably a bad choice. There exists one labeling such that AS is good with respect to x1 or xn. I want to say something about the summation of xi's. How many labels we need to pick on average? Is this fine? So if I have x1 to xn, the number of proper assignments that are there is at most right? And for each of them, I can only have these many ASs that are good. So yeah, you will get a bound on how many xi's need to be from this. Let me write it down. Is this here?
So
What I'm
xi is like a list.
It's a list for
each edge, for each eye, you have a list of assignments.
right.
Okay.
And now
Per edge, right? Yeah.
And now I'm trying to put a lower bound on how many of them there needs to be in order to have all the ASs satisfied. And the way I'll do it is a very simple counting, which is look at all possible unique assignments you can generate from them is going to be the product here. And each of them on their own can satisfy only these many.
Okay.
So there just needs to be a lot of those, which is, can I use this symbol epsilon, maybe delta for this? So we have summation product. Should be greater than or equal to 1 over 1 minus delta. Right? And this implies that I can just make this to be at most x to the k, where x is the sum of these things. Just a very weak bound. And think of delta really as
Yeah,
very close
to
to,
one.
yeah, think of delta as very close to 1.
Something happened to the K.
Sorry, 1 over K.
Okay.
Think of delta as very close to 1. In fact, think of delta in your head should be like 1 minus 1 over K to the K. So when you substitute back here, you get 1 over K. Or K, X is at least K. Right?
Okay.
And I claim that from this, we can go to set cover using standard reduction. I can show it, but we can go through. And this translates to be the set cover size in the no case. So in the yes case, you need K sets. In the no case, you need at least K square sets. So, but this is where the gap translates to. And all we did all along was just use some basic error correcting code.
And this kind of switch from rows to columns.
Yeah. I don't know if you remember this, but this way of calling it rows and column was yours.
No, I don't remember, and I don't.
So when you write there, you mean M?
Sorry?
When you write there, you mean.
Yeah, to me they're roughly the same. Yeah, I mean I can get M.
Sorry, what's the blow up in the parameters in this reduction?
So far, the blow up is going to be here Q, the alphabet size. The distance will be roughly 1.
The alphabet size has to be some like K to the K.
Yeah, but it's just some function of K.
Yeah, I realize this, but
to get the gap of K, I need to go exponential.
K to the K.
So the point is, this way I can push it all the way up to log n to the 1 over K and keeping this side size log n. And then there is the standard reduction from phi gain, which basically you translate this instance to a set cover instance, where every variable on the left and an assignment to it becomes a set. And everything here on the right, you sort of choose for every assignment it gets which neighbor it checks with. And that is going to be a universe element, right? Formally, but that's what we'll try to do. So I'm now going to set cover. So I'm taking this instance.
So you want to convert like this kind of consistency CSP to a set cover instance?
Right. Where in the yes case, the list size is basically what matters. Whatever you need in the yes case, the list size will be the set cover size. And in the no case, we'll need at least these many. And the way to do it would be my universe is just pick a variable here, any one. So let's say AS. And then I have a function which takes every possible assignment to it and checks it edge with one of the neighbors. So it can be written as a function to, for all S and F. So every universe is a pair. So in other words, you have a subuniverse for each of these things, which is all possible functions from this labels here to a neighbor. You can think of it as the hypercube partition system.
What's the meaning of these functions? What's the intention?
So you can look at this function space as a hypercube, and you want to pick dictators which sort of.
How is this a hypercube?
So these are points in space M to the sigma call.
Okay.
And so that you have sigma call many dimensions.
Okay.
And M is your thing. And suppose I had a specific dimension in which, so let's say an assignment to AS was some alpha. And this alpha satisfies all my constraints. So when I go here, if this was beta, then this thing is satisfied. That means all those functions which map f of alpha to beta, or f of alpha to E1 will be satisfied. That's what I want to get.
Okay.
Let me first write down my sets. My sets are going to be basically EI comma alpha, where I is in M, alpha is in sigma E. So every variable and its assignment is a set. And when does, let's pick someone, AS comma F belongs to S EI comma alpha, if and only if there exists a labeling of AS, there exists some, let's say lambda, 1 to lambda k, which is a labeling for AS, such that f of lambda is pointing to EI. And if I look at alpha comma lambda, it satisfies the constraint. See, let me write EI comma ES. So this is the set system. Let's see the yes and no cases. In the yes case, there is an assignment to each one of these and each one of these, such that everything is satisfied. So if I pick the representative sets, then I want to claim that I cover every universe element. So there is, let's say, some sigma E. Let's write this situation. So sigma call. Such that all the constraints are satisfied. So now pick the sets, the following sets, which is S E1 comma sigma of E1, S E2 comma sigma of E2, S EM comma sigma of E. These are the M sets. And now take any arbitrary universe element. So this is an arbitrary universe element. I claim that it belongs to. So now look at f of sigma call. Let equal to lambda. Then this belongs to whatever, f of sigma call of this should be a number, say I. Then this belongs to S EI comma sigma of Z. That's it. So that completes the yes case. In the no case, suppose there was a set cover. And I don't know, I picked some bunch of sets from E1, some bunch from E2, and so on and so forth. But at the same time, I can interpret it as a list labeling. But I know for the list labeling, if the size was less than this, then there is some AS that is not good. So let's say A star S is not good. What does that mean? It means that for every label, there is some constraint that fails. It's that for all lambda, there exists an I. such that constraint is fake. I think that's it. And this gives me a way to build the function, which will be just look at f of lambda and point it to that specific I, and that universe element will not be covered.
And this will be for how many, for what M, for what cover size?
So you will get this is the set cover size lower bound.
The K to the K.
Yeah, I mean, we'll make it even larger.
Yeah, you can make it arbitrary without it paying it.
Is you'll get any function of k
Any
from
kind
this,
of K you want, yeah.
and you can get all the way up to log n over 1 over poly k. Why do we stop here? Is because after this, the universe size is super polynomial. The universe is exponential in the right alphabet size. And so we can get all the way to log n over 1 over poly k, which for any fixed constant k is nice. It's a log n to the epsilon kind of lower bound. So this clarifies one aspect of one of like the open questions is to get omega log n, and the main challenge there is we want two things.
Before you go there, so just digest a little bit. So kind of one way to interpret this is that gap hardness for set cover has a much kind of more direct proof. You don't need to use PCP machinery.
Right.
So what do you interpret it? So, and you gave us this nice picture of this W hierarchy with these, constant depth gates, circuits, and these high fan-in and low. So how do you have an interpretation of that? Like you can blow up W2 things in an easier way, or?
In general, anything outside FPT, you can blow up with any function of k. Here we're blowing it up by 2 to the k.
No, I meant blow up. I meant like make it robust, make it have a gap.
Right. So there is this way of looking at it, but then there is another way to look at it which makes this point very clear, which is as long as k is less than log n, there are certain techniques that sort of work, which don't work beyond log n.
Let's see. And for vertex cover, I mean, K, the interesting K would be
linear enough.
Yeah.
So there are all these things. It has something to do with the fact that there are, say, almost k-wise independent sets. Where k is less than log n, you can construct things very efficiently. So these are interrelated because you use those objects. I mean, an error correcting code is some weak version of almost k-wise independent set. And this property is used in a different proof, it's more obvious, but this proof it's there too.
Okay, all right.
And yeah, getting rid of this has nice analytic questions. For instance, I don't want the list size. Here it's some function of k, right? So this 2 to the k will hurt me. Always I need to pay 1 over k. I can't blow up to log n. So can we get here 2 to the k and the right alphabet size versus the list size? If this is 2 to the k, I want here to be 1 minus delta. Or I get some constant alphabet there and I'm okay with this.
You're now saying like an open question here?
Right, to improve it to omega log n.
You believe omega log n should be true?
Yeah, this I believe is true. This leads to this question. Also, parallel repetition theorem is mostly meant for like the max case, whereas I would want the list size case as well. And there is nothing you can take off the shelf for these things.
So say again what you would need, what would give you this result?
If the list size is constant, I want the right alphabet to be constant. And then I want a parallel repetition theorem that if I take r repetitions, blows up the alphabet by r, but also the list size lower bound goes up by r in the exponent. And if such a thing exists, then good, we get omega log n. But a lot of ideas, like simple ideas, just break for these things.
But what happens if you wanted to start with a set cover problem, just a normal set cover problem, and reduce it to a set cover problem with a gap?
That's the talk in 3 weeks.
What?
I'm going to talk about it in 3 weeks. But we can do this. This is the surprising thing.
Okay.
That
So you go through to CSP or
directly. There are ways to do it directly and with CSP as well you can do, but you get weaker things. So how much am I doing with time? Not good. How much time do I have?
You can go until, let's see, time is it? You have 20 more minutes, let's say. Is that good?
No.
You should haggle?
You should haggle, like you should negotiate.
Okay.
No, I just continue talking until you feel, it's okay, impolite, but I don't care, I will leave. So let's try doing it for clique, the same thing. So what we did before was this. I think it's instructive what I'm going to do now. So it was some 0, 1 to the log n.
So now you're gonna prove for us some kind of hardness gap click problem for
Yes.
gap.
Starting from exact to CSP. We encoded like this, but there's only so much we could squeeze in terms of CSP. So the natural thing to do is encode like this. The issue is, of course, when I encode like this, I still have some very weird membership things which are here. I need to somehow capture them here. So the first thing is, what if the constraints here had a linear structure? Then, okay, if I take some subset of k here, I can just take their sum as the assignment, and somehow I can capture it using some constraint. So we are going to, if you work a bit on CSP, then you can get this linear structure. So I'm going to assume the following, which are called vector CSPs. Where the alphabet, I'm going to think of it as some fq to the L. So L is going to be log n and q is some function of k. And now, moreover, I'm going to say take any edge E. It's not going to be a pair of sigma, but just sigma. So it's some subset of q to the L. And the goal is the two vertices, are they assigned 2 points whose sum falls in the set. So if E was u comma v, then alpha comma beta belongs to CE if alpha plus beta belongs to CE. So we can start from this CSP. There's no to be W1 hard, CTH hard, so we can get this. Okay, once we have this, then we can talk about Hadamard codes. So I'm going to take the Hadamard code of this thing. But what is the word called parallel encoding? I should do some justice to the word parallel PCP.
Well, this was in your top title, so
Yes.
we deserve to hear about it.
So one way to look at it is you can squeeze this whole thing and look at it as one alphabet symbol. But then if I do that, my alphabet size is n. And then if I take a Hadamard encoding of that, it's 2 to the n. Like it's too long. So what we will instead do is we will break it down into elements of f, which is just some function of k, and encode this using Hadamard. But all of them parallel. And any testing we want to do, querying, if I'm looking at this specific thing and I'm querying in, say, this and this location, I'll be querying the same location everywhere else. So I'll get this back. So this is called the parallel encoding. You can take any error correcting code and define this parallel encoding. So if this length was L, then this is L parallel encoding. Right? And then the question is, how is this useful? This is some way to circumvent the issues we had with the CSP and not be able to handle any constraint. Because now this itself, I can build PCPs on this, do things on this thing. As long as I somehow have a way to simultaneously have consistency across all the parallel things, we are in a good shape. And this is what is achieved eventually at the end. But let me show it for clique for now. Okay, so the CSP I'm going to associate, so everyone knows Hadamard code. Okay, hopefully. Otherwise, it will be implicitly defined in the construction. So we're building a graph H. Let me actually see it as a CSP. So this is some, I start from B comma U, so from sigma prime.
You wanted a click, so you're doing a CSP and then you will.
Yeah, I will just interpret that CSP as it is as a clique instance by just taking the label extension. And I will, argue about things based on the satisfying assignments of the clique based on the CSP.
Label extended, this is like the FGLSS.
No, just label extended. I'm not interpreting the constraints. So if I have k variables, then I'll have k super nodes, and each one label will become a node in that.
And you connect to if they're consistent.
Yeah. If they're doing some test.
Okay, fair enough.
You will see there is I'll be using some hack in this thing.
Okay.
So we know that Hadamard codes are locally testable using 3 queries. Right. So for every A, B in FQ to the K, we can look at A plus B, and then the function should be the sum, the homomorphism. Our vertex at A is going to be FQ to the K. Okay. And now for each of this, I also need to associate what its alphabet is. So sigma prime, since it's an L encoding, I'm doing L of them simultaneously. So I just encode it with the triple. So mentally, we can think of it like this. So here I have a node. Here I have a node. This node is indexed by A comma B, which are 2 elements in FQ to the K, which is basically I have checked if this encoding at f of A plus f of B is equal to f of A plus B. Right? And f of A is going to give me an entry here, but it's L. So it's going to give me all the entries in all the L encodings. And all the triples where it's equal, I put them as valid assignments here.
Yeah, a bit lost. The starting point is, can you?
I start from 2 CSP.
With that special structure.
Yeah. And now I'm just doing encoding using Hadamard code.
Right. So what is a capital A and capital?
So I'm encoding using Hadamard code. And now my variables are going to be all possible queries of randomness. Like for all possible randomness, the randomness is defined by a pair, right?
So, sorry, the L parallel encoding means you encoded every column that had length k
Right.
by all the linear functions, which has length like q to the k.
Right.
Q is not 2, some other q.
Let's do
It's 2.
Let's
So
do
just 2 to the k. Okay.
Yes.
Okay, so now you have a row for every element in F2 to the k.
Yes.
Okay, now you're building, that's on that side. Now you're building what?
A new CSP.
A CSP you're
Yeah.
building? Oh,
A
okay.
CSP where a variable corresponds to an enumeration of a random coins of the local
Right,
testing.
so the test needs to choose 2 points, and
Yes.
so capital A is all possible choices of 2 points.
Right.
Uh-huh.
And now the alphabet is what you would see when you query in those 2
Right,
points.
these are the
plus a
answers.
third. Yes.
Yeah, okay,
Third point, which is sum of the 2.
right.
And
So-
it's going to be an L tuple.
Yeah.
L tuple, L tuple.
So but it's still all f to the L times f to the L times f to the L, or?
No, it's a subset. Like you only allow a certain subset.
It's really-
So it's f to the L times f to the L, and you interpret the third coordinate as like 2 plus.
Yeah.
Right,
Okay.
okay,
Alpha, beta, alpha plus beta.
okay.
Sure.
Mhm.
It's confusing when you write equal to f to the L 3 times because
For example, okay.
And then I have one alphabet for each of them. It's the same part, you can relate. But this is my variables, and now I need to tell what are the edges. It's easier to tell what are the non-edges. Whenever it's not consistent, you don't put an edge. So I'm simultaneously interpreting this as a CSP and as a graph, where the graph is just all the possible labels that are there, and edges correspond to consistency.
What are the right-hand vertices?
There are no right-hand vertices.
What's that other circle?
Oh, this is just another node.
Ah, these are nodes,
Yeah.
okay,
A prime, B prime.
got it.
So what's B? Capital B?
B is the edges. Maybe it's a bad sign. Let me use that, maybe. Or E prime, whatever, like something for edges.
Okay.
Good. And now I'm checking consistency, right? So if I have some alpha beta here, alpha plus beta, and I have some alpha prime, beta prime, alpha plus beta prime. If they have a variable in common, they should assign the same thing. That's my consistency. So that part is clear, right? So consistent assignments. The second, so this is where the trick comes, which is if I take some A, B here and some A plus EI and B here, or A plus EI plus EJ and B here, I can decode back what the ith and jth rows are.
Well, what is EI? There is unit vector now, or that?
Yeah, unit
It's
vector.
not there before, it was the.
Oh, sorry.
IS.
So if I had a variable A comma B and let's say A plus if I had this and this, then if I look at their assignments, I'm going to get what the ith and jth row are, the sum of the two. Right? And if that constraint is satisfied, it better belong to Cij. So the decoding, I explicitly just enforce it like this. And I'm using the fact that it's 2 query.
So you mean you're putting a constraint on these two nodes, A, B, and A prime, B prime, not only to check consistency, but also to enforce
Membership.
the implicit constraint that you're able to enforce.
Right.
Well, what's this INJ? For which INJ
For every
forever?
INJ substat belongs to E, which is the original constraints.
But A prime here is equal to A plus EI plus EJ. So
Yes.
for those nodes, you put this constraint.
And that's it.
Mhm.
And now, what I want to say is that in the yes case, you will, and the graph I associate with this is just take the extension. So the graph is going to be G prime, whose vertex set is just and then whatever, if they are consistent, you put an edge, otherwise don't. If that satisfies this constraint, you put an edge, otherwise don't. That's it. And I claim that you can't say anything much about the CSP in the no case here, but you can say something about the clique. Okay, so that's where I want to go. Yes.
Is it possible to use the linearity over here to somehow like test the linear combination edges as well? Or I'm not quite parsing all representation.
So every edge here, the constraint is of the form the sum should be in some set.
Yeah.
And I can decode what the sum is.
Is it possible to like decode the sum here and the sum? I was thinking we could maybe have like IJ as an edge and like I prime J prime as an edge. Could you like decode both? Oh no, okay, I see.
You can decode the sum.
You can decode the sum of the
these
two things. Or
Yeah.
But then
some of the two predicates.
you don't know, how to.
Yeah.
Okay, so this much we know. So in the yes,
I guess for
The
all
CE with like a
edges,
subspace for
yeah, for
every
all edges that CE is the same for them, you can
subspace.
do it.
It has to be a subspace.
Yeah, wasn't it oh, it's a set? It's not even a
just
subset.
yeah, it's not some.
Yeah,
Okay.
If it's the same subspace.
Right. Great.
But you're going ahead. It will become a subspace if I have time to talk.
Ah, yeah. Let's see. You have 5 minutes and we'll give you an extension.
Yeah, I'll talk for 5 minutes about the proof, and then the extension I'll tell the other result.
And the next proof.
No, the next proof is not. So clique, in the yes case, we have, you pick one assignment for each of them. So you have a clique of size 2 to the k square or 2k? 2k.
Yeah. Oh no, we have a gap problem. At 12:30, there's gonna be a huge line. At the lunch, okay, so.
I see.
That's all I can do about it.
I'm gonna continue writing.
So you can go on until 12:40.
Can bring our lunches here.
Yeah, sure.
So D is the clique of size. Think of delta as small, like less than 1/20. So suppose there is a clique of this size. Then from linearity testing, we know that there exists some function, which is a proper code word, which is delta close to this. Right? So there exists some, and the claim is, so there exists some fx. I think of x as in k times l, this whole matrix, and fx is it's just encoding on everything. Let's just think of linear functions such that fx minus t whatever you interpret this as. Now, the other claim is that if you look at D and how many variables it hits, I want to claim it's large. This requires a proof, but believe me for now. So now I can define a function which is some G, which is on the variables that contain here and agree with fx. And from this function, I want to claim that I'm able to decode an assignment which satisfies all the constraints. Because if you take a constraint and I want to decode it as EI and EJ, I first pick a random A. This random A falls in the good case where everything works with some nice probability, 1 minus 3 delta or something like that. And then what is the probability that A plus EI plus EJ also falls? It's another 1 minus 3 delta. So 1 minus 6 delta, I'm good. I've managed to decode it. And I'm able to check, and it's an edge in my clique, means that it satisfies this constraint. So I'm hard-coded it into the graph. So yeah, I'll be able to satisfy all since this is true for an arbitrary constraint I picked, I'm found a satisfying assignment. That's the whole proof. Modulo sum writing.
And this, can you amplify this using heuristic coding or?
Okay, yeah. So now, yes, you can. You can push it all the way up to saying if there is a clique of size k, finding one of size k to the 1 minus little o of 1. Say k over log k, k over polylog k, using list decoding of Hadamard codes. Yeah, you can do that. Pushing it beyond, say k versus square root k, doesn't work through this mechanism. Okay. So the last thing, how much time do I have?
I mean, I think you should probably summarize. I mean, do you want to state a theorem statement? Or?
Yeah, let's do one theorem statement.
And then you can summarize.
Then, yeah. Okay, so the state of the art, which sort of is like the strongest result we know here, is due to strong events. Do you know whom I'm missing?
As.
You are here.
As.
Without me and this combined thing, which says that for all epsilon, no, and assuming ETH, so we are not assuming any cap. There is no n to the k over polylog full-time algorithm. Which takes us input at 2 CSP and distinguishes, yes, there is a satisfying assignment, and no, there is no assignment that satisfies even epsilon fraction of the process. Uses, so the way it works is in 3 steps. You get the Benson-Sudan PCP in this regime, and you go to 1 versus 1 minus polylog. And then use the HDX routing to get it to 1 versus epsilon, 1 minus epsilon, and the de-randomized parallel refutation to get this. The last two just work off the shelf because there the blow up in alphabet is nice. The first one, yeah, also works but needs some work.
I think you can get sub-constant epsilon.
Yeah, that's for FPT. You will lose here.
Okay, yeah, but for some sub-constant they don't lose, I think.
Yeah, but I don't think even they analyzed it for the HDX thing. For some sub-constant, right?
Okay.
So yeah, this is, and everything I've said follows from this. Then you can assume just ETH.
Okay, thanks so much for